This next talk by Daoping Zhang, who's also a year 3 PhD from Liverpool. So Daoping look at this more theoretical side of the image registration modeling on the quality of the registration map. This is something we don't normally think about it. We just plug in the model, like Modern Young wrote Oxford University Press book 2004, where there's no such thing discussed. You just do it. Look at the quality, it looks fine to me, and get on with it. Last 2 years, a couple more papers talking about how to ensure the map is diffeomorphic, and then it turns out there are quite a few works published last, say, 10 years. And so here he's trying to look at this thing more systematically to see what's the best way to put a constraint on your existing model to make sure it's diffeomorphic. You can I think one easy way I try to explain to colleagues who are not familiar with this, what if I tune my parameter to avoid, say, folding or mesh tangling? That's fine, but within the model, you are not achieving the best registration. You are compromising. In other words, if you think about it, if you don't register, you have uniform mesh. That's the best quality you can hope for, but it doesn't do any job, right? Usually for large deformation, you want to deform more within your model. You want a more a fitting term to be as small as possible. The mesh quality will deteriorate somehow. So you need some quantity to constrain it. So I leave the detail to help you.
Thanks for introduction, and I'm glad to be here to give a presentation about my work. And this work is joined with my supervisor presentation. And my talk has 4 parts. Firstly, I will give a short introduction about image registration, and then we focus on how to get diffeomorphic registration and propose our new constraints. And finally, I make a conclusion and list some of our future work. And image registration is to find an optimal geometric transformation between corresponding data. It has a wide application in medical imaging, computer vision, and remote sensing. And according to this definition, we can build its variational framework. And firstly, we give 2 images. One is called reference, and the other one is called template. And in order to measure the difference between the deformed template and the reference, we should give a fidelity term. And in order to make the problem well posed, the regularizer is indispensable. So here, D is the fidelity term and S is the regularizer. Alpha is the parameter to balance these 2 terms. U is the displacement and Y is the transformation. So for the fidelity terms and regularizer, there exist many choices. And here I just show a very simple example, a diffusion model. And here the first, the first term is sum of square differences, or we call it SSD. And the second, and the regularizer is a typical W12 seminorm. And for solving this variational problem, we can get its Euler-Lagrange equation and then solve this resulting PD equation. Or we can directly discredit this variational problem into a finite optimization problem, then use some suitable algorithm to solve this resulting optimization problem. And many relevant applications, such as medical imaging, require that plausible transformations are diffeomorphic. Namely, we should find a smooth mapping with a smooth inverse. And this figure has 2 meshes, and the right one is smooth and no folding. The left one. The right one has folding, so we could not find the smooth inverse. So the left one is, we hope to find the mesh like the left one. And so, however, not all models can produce the diffeomorphic transformation. So, in order to overcome this difficulty, we can control the Jacqueline determinant of the transformation, because according to the inverse theorem, the inverse function theorem, Jacqueline determinant larger than 0 guarantee a local bijectivity. So we can add this constraint to the above mentioned framework to get this new framework. And here as one, we can think it soft constraint. Another method to get the diffeomorphic registration is large diffeomorph Diffeomorphic metric mapping, or LDDMM. Here, the deformation is modeled by its velocity over time according to the transport equation. And recently, a new technique, which is to control the Beltrami coefficient, is used to get the diffeomorphic registration. When the infinity norm of the Beltrami coefficient of the mapping is smaller than 1, we can ensure that this mapping is diffeomorphic. So based on this point, QCHR model was proposed in 2014, and here it directly regulates its Beltrami coefficient, not displacement like a diffusion model. And here, this model also allows the user to provide the landmarks. And motivated by the Beltrami coefficient, we propose this new regulator. And we can find its relationship with the Jacobi determinant. That is, this term is smaller than 1 is equal to the Jacobi determinant larger than 0. So here we add this new regulator to the diffusion model to get a new model. And our model has two main advantages. And firstly, we control the Jacobi determinant of the transformation indirectly. For the traditional method to control the Jacobi determinant, we can restrict it into a specific interval or make it close to 1. But sometimes it is very difficult to define this interval, or it is not suitable to make it close to 1 when we don't want to preserve area or preserve volume. So our model doesn't need to make this restriction. And another one, we reduce unknowns and simplify the algorithm compared with the QCHR model. And for the algorithm of the QCHR model, it deals with two main unknowns and one auxiliary unknown. And in each iteration, it needs to solve two linear systems. And due to the non-convexity of its original problem, the convergence may not be guaranteed. So through reducing unknowns, we just deal with one variable's displacement, not Beltrami coefficient. And in each iteration, we just solve one linear system. And based on this point, we can save storage and computing time. This is a synthetic example, a big disk to a small C shape. And the red points and blue points on the template and reference are used in the QCHR model. And this page is the result, and we can see our model can get a good default template. And since the template and the reference have significantly different area, the hyperelastic model fails. LDDMM can produce a good result, but it costs a bit more time. And diffeomorphic demons may seem to trap into a local minimum. And here we use 20 pairs of landmarks, but QCHR model still cannot get a good result. Here, diffusion model produces outlier, and its mesh it has folding, and so it's not diffeomorphic. For the other 5 methods, they can produce diffeomorphic meshes. And this is a pair of anonymized CT images from the Royal Liverpool University Hospital. And here we want to compare the changes of our interested regions of abdominal aortic aneurysms with stents inserted inside them. And here the a small white region on top of images help us to find the correct slice to compare. And this is the result, and we can see our model can produce a slightly better result. And here, maybe the diffusion model can produce visually better results, but the mesh has folding and non-diffeomorphic. So here we want to find the diffeomorphic registration and to produce accurate results. So in this talk, we propose a new constraint, and based on this constraint, we propose a new model, and this model can produce accurate and diffeomorphic registration. And for our future work, we want to find a fast solver and consider how to extend our idea to 3D registration. Yeah. That's all. Thank you.
In your comparisons, how did you set your regularization terms for the different algorithms? And did you spend more time setting your own regularization than the regularization for the competing methods?
Oh, so we have used some measurements like relative SSD or JSC, and yeah, maybe the two main measurements. And JSC is a Jacob similarity coefficient. Yeah.
Jacob, you mean the initial guess, if you like.
Yeah, getting the guesses for the various regular, the alphas and lambdas and stuff that go into these algorithms, because I never look at the evaluations of, say, MICI or various other conferences. I want to see, what the algorithm is, and the evaluations are generally just a measure of how much effort someone's gone into tuning their parameters.
Yeah, the robustness of the parameters.
Oh.
I think we did like similar to what Mike was showing for the segmentation. For each model sort of compared here, we sort of find out the range of parameter where you produce a decent result, and then select one representative or the best one for their model to be fair. Otherwise, but for initialization, it's tricky. For a lot of models, they're right. If you provide a zero deformation to start with, most on the same resolution, most algorithms wouldn't converge. You really need a multi-resolution idea, like low resolution up to 16 by 16 or something, work all the way up to get a good initialization, given the parameters are correct, and then for them to converge. Because registration models are non-convex, they're very tricky.
Yeah. It's setting the regularization that's tricky thing.
Yeah, comparison, you're right, can be tricky. Any more remarks? So essentially for Daoping the model, you don't have to assume, you don't have to know enough about your pair image. You don't say, I think the object I care about, they are more or less have the same volume, same area, therefore this model is good, this constraint. So you don't do that. You just say mathematically, if the determinant of Jacobian is positive elsewhere, anywhere, I'm fine with the quality of the mesh. And then here, it does that by just control this complex quality, translating the real variables, this determinant coefficient, which from differential geometry. We have a couple of pure colleagues interested in this. They said, let me think about a similar quantity in 3D. We are working on it, and then in 3D, complex variable don't work. So you think of other similar quantity control result. Okay, thanks, Daoping.